El Instituto de Investigaciones en Matemáticas Aplicadas y en Sistemas les da una cordial bienvenida a el tercer día del coloquio del Centro Virtual de Computación 2018. Para comenzar, nos congratulamos en presentar la ponencia magistral Quantum Computing and the Limits of the Efficiently Computable. Para brindar esta ponencia, nos hace el honor de acompañarnos el Dr. Scott Aaronson, del Quantum Information Center de la Universidad de Texas. Antes de comenzar, brindaré una breve reseña sobre nuestro ponente. Dr. Scott Aaronson es doctor en Ciencias de la Computación por la Universidad de Berkeley, en California. Trabajó en el Institute for Advanced Study en Princeton, New Jersey, en el Institute for Quantum Computing en la Universidad de Waterloo, en Ontario, Canadá, y en el MIT en Cambridge, Massachusetts. Sus principales intereses de investigación se centran en los límites fundamentales de lo que puede ser eficientemente computable en el mundo físico. Implícitamente, estos intereses lo han llevado al cómputo cuántico. El trabajo del Dr. Aaronson en este tema incluye las siguientes aportaciones: limitaciones de los algoritmos cuánticos en el modelo de caja negra, la capacidad de aprendizaje de los estados cuánticos, pruebas cuánticas y consejo, el poder del cómputo cuántico post-seleccionado y cómputo cuántico con curvas temporales cerradas. Finalmente, cómputo lineal y lineal óptico. Actualmente labora como profesor de Ciencias de la Computación en la Universidad de Texas y es director fundador del nuevo Centro de Cómputo Cuántico de la misma universidad. Sin más que agregar, démosle una cálida bienvenida al Dr. Scott Aaronson.
Okay. All right. Well, muchas gracias for inviting me here and for the for the kind introduction. I was proud of myself that even though my Spanish is so poor, I could more or less follow that. But So I wanted to, and thank you for coming so early in the morning, also. So I want to tell you about quantum computing, which is my main interest, and the limits of efficient computation more generally. Now, when I did and you can find survey articles and many other things if you want to learn more on my homepage. Now, when I did a Google image search for a quantum computer, this is one of the first things that came up. I'm a theorist. I'm not an engineer. I don't build the quantum computers. And even when they take me on a tour of the lab, they're very, very nervous that I'm going to break something. Okay, but I don't think that this is what they look like. Okay, so, the labs I've seen haven't looked quite like this, but my starting point will actually have nothing to do with quantum mechanics. It's just, what are the ultimate limits of computation? So, we've become very used to Moore's law, which says that just about any measure that you can name of computing power has been increasing exponentially with time since the computer industry really started in the 50s or 60s. Number of transistors, the number of clock cycles, amount of memory, and so on. Okay, we know that this cannot continue forever. Okay, and in fact, by many metrics, Moore's law has basically already stopped. Right, the transistors are no longer getting much smaller. For example, now if you want more speed, people have to resort to using more and more cores or more parallel processors. But there are limits to that as well because of things like communication latency. Okay, so you could ask, where is all of this going? Well, I have many friends, especially who I talk to whenever I visit the Bay Area, who think that, well, this may end, but not before we're able to build computers that exceed the raw processing power of the human brain. Right, we're not quite there yet, But by some measures of processing power, we may be there within the next decade or so. And many of them say, well, it should just be at that point a matter of running a deep network on the on the GPUs and the sort of cloud computing resources that will be available in 10 years, and we see no reason why you won't then get a super intelligence that will maybe even exceed the power of the human brain. Right? What happens then? Well, of course, the robots taking over the world. Now, I don't know if this will happen or not. I actually have a bet against a friend that this will not happen in 10 years. I was very surprised that he was willing to take this bet, because I feel like in any world where I would have to pay the bet, that having to pay it is the least of my worries. Okay, but in any case, even if AI does come and, exceed the intelligence of humans, to a theoretical computer scientist like me, in some sense, that's not even so interesting. Right? I mean, what is a super intelligent robot, right? It is yet another Turing machine, right? It's yet another, device that would operate according to the same principles of computation that we already know, that have been the basis of computing since the beginning. Maybe the same principles according to which our brains also operate. What this talk will be about is sort of, can you go beyond that? Do the laws of physics allow you to do computation in any way that really exceeds what could be done even in principle with computers that we have now? Okay, now there are sort of fundamental beliefs about that question that have been at the heart of computer science since its beginning. Okay, famously, there is the Church-Turing thesis, which, in its modern form, I would say, says that anything that is computable at all by any, say, physical device is also computable by a Turing machine, which is the mathematical idealization of what we mean by a computer that was invented by Alan Turing in 1936. That, it involves a paper tape with squares and a tape head that can move back and forth across the squares. The actual details are not so important, precisely because of this Church-Turing thesis, which says if you try to invent any other kind of computer, whether it's a Mac, a PC, the phone in your pocket, or even a computer made of billiard balls or something like that, then some will be faster, some will be slower, some will have more memory, and others less. But fundamentally, they can all simulate each other's operations, right? It is all the same kind of soup, right? They can all emulate each other. Okay, and in this sense, there is only one mathematical theory of computation. I mean, when I first learned this, like as a teenager who learned about programming, this completely blew my mind. It was like learning where babies come from. Okay, why didn't anyone tell me earlier? Okay, but now going even further, there's what we could call the extended Church-Turing thesis, or the polynomial time Church-Turing thesis, which says that not only can all of our different notions of what a computer is simulate each other, and in that sense are equivalent to each other, but the simulations are reasonably efficient. Okay, they may induce what we call a polynomial overhead, meaning something that takes linear time on one type of computer might take quadratic time on a different type of computer, but it's not going to require exponential time. Meaning the number of steps. We're talking about how rapidly the number of steps grows as a function of the size of the input that you're given, right? And we're very, very interested in computer science and what can be done in a number of steps that increases only like a polynomial function in the size of the input, like only linearly, only quadratically. That is our sort of rough approximation to what can be computed in a reasonable amount of time. Like, let's say, before the end of the universe. Okay. If something takes exponential time, then very, very quickly, even when you got to inputs of size 1,000, you could easily, have a computation that would could never be completed before the whole universe had degenerated into black holes and radiation. Okay, so we don't want that, right? And this extended church Turing thesis said, well, anything that could be done efficiently with one type of computer could also be done efficiently with another. Okay, so to give you a foreshadowing, quantum computing does not challenge the original church Turing thesis, right? Everything that is computable by a quantum computer is also computable by an ordinary classical computer. But it does severely challenge this extended thesis. There are things that can be done efficiently with a quantum computer that we believe would take longer than the age of the universe with any existing computer. Okay, and that is certainly one reason to be interested in this subject. Even if you didn't know or you didn't care about quantum mechanics, that is a reason to care. Okay, so but let me. Before I even come to quantum computers, let me just talk about what made computer scientists so confident of this extended church Turing thesis in the first place, right? I mean, what happens if you try to invent a new type of computer, that some other type of computer that would do things, dramatically more quickly than any existing computer, right? What goes wrong with it? So let me just give you a couple examples of other ideas people have had of how you could use physics to exceed the known limits of computation. And what goes wrong when you try. Okay, so my first example will be the relativity computer, right? Everyone talks about quantum computers, but why not the other great theory of 20th century physics? So the idea of a relativity computer is very simple. It is that you start your computer, working on some very, very hard problem. Could be the traveling salesman or some NP-complete problem. You've heard of that. Could even be a harder problem. Then you leave your computer on Earth, just grinding away on that problem. Then you board a spaceship, okay? And you accelerate the spaceship to very, very close to the speed of light. You fly around for a while, and then you decelerate, and you return to Earth. Okay, now, Einstein tells us that in Earth's frame of reference, billions of years, may have now passed, right? So all of your friends are long dead. Civilization has collapsed. If it didn't already collapse in 2020 or so, I'm a little worried that our president is going to do that. But if you can still find your computer and if it's still connected to a power source, then you can find the answer to your hard computational problem. So to me, this raises an immediate question, which is why doesn't anyone try this? I mean, if you're worried about your friends, then just bring them on the spaceship with you, right? So I think there's actually a very, very interesting answer to what is it in fundamental physics that would rule this out, and the answer has to do with the amount of energy that it would take to accelerate to relativistic speed. Okay, you can do a calculation which says that if you wanted an exponential computational speed up by this sort of means, then you would need to get exponentially close to the speed of light. Right, like c minus 1 over exponential. Okay, and to do that would require an exponential amount of energy. So in effect, we've traded one exponential resource for another one, right? We now have to worry about, well, don't you need to spend exponential time just fueling up your spaceship before it takes off, right? Where do you find an exponential amount of rocket fuel? Or maybe, you could find some super compressed fuel, but that leads to problems of its own. So it's a beautiful example of how if you look at only one or two laws of physics in isolation, it can look like you get so-called hypercomputing powers, computing powers that would exceed what a Turing machine can do. But you really need to look at all of the laws of physics that we know together. Okay, so another such example is what I'll call the Zeno computer, after Zeno's paradox. Now, this is simply a computer that would do the first step of its computation in 1 second, the second step in half a second, the third in a quarter second, the fourth in an eighth of a second, and so on, so that after 2 seconds it would have done infinitely many steps. Okay, that would be a very powerful computer. It could even solve the halting problem, for example. Deciding whether some program would ever stop running. That would mean it could could tell you the truth or falsehood of the Goldbach conjecture and the Riemann hypothesis, many other famous questions in mathematics, because it could check infinitely many cases in only 2 seconds. Okay, again, well, why doesn't anyone try to build that? Well, in some sense, there are people who try. There are people who overclock their microprocessor, right, and run it much faster than the recommended speed. But some of you might know the danger in doing that, which is that if you run your processor too fast, it will melt. Okay, this is why computers have fans in them, right? And there used to be supercomputers that were actually cooled with liquid nitrogen or liquid helium, so they could be run much faster. I don't think that's very economical today. Okay, but again, you could ask, what are the ultimate limits to this sort of thing? Well, as you wanted to run your processor faster and faster, it would need more and more cooling. Okay, the cooling would once again cost more and more energy, right? We again see energy as a limiting factor. Okay, now, once your computer was running fast enough, you might as well forget about the cooling and just talk about the energy that is inherent in the computation itself. Okay, now, so is there a limit? Well, according to known, we don't know exactly, but according to known physics, it seems yes. Namely, if you wanted to run your computer faster than 1 step per Planck time, okay, which means 10 to the 43 steps per second. The simplest model of such a computer would be, let's say, a photon that would bounce back and forth between 2 mirrors that were only 1 Planck length apart, so 10 to the minus 33 centimeters. Okay, but now if you calculate the energy of such a photon by E equals hv, Planck's equation, then what you find is that the energy of that photon would exceed its own Schwarzschild radius. Okay, for those who don't know, that is just a fancy way of saying that your computer at that point would collapse to a black hole. Which I've always liked as nature's way of telling you not to try something. Okay, but what about quantum computing? You knew from the title that it was coming. These are supposed to be some spin 1/2 quantum particles. Again, I don't think that's really what they look like. Okay, now in order to explain what a quantum computer is, because when you first read about it in the popular press, it sounds almost as crazy as those other things that I just described, right? It sounds like science fiction. And yet, we know that there are today experimental groups all over the world, at Google, at IBM, at Microsoft, at university labs all over the world, who are spending considerable money right now trying to actually build this, right? So what is the difference? Why is this more realistic or less science fictional? Well, to explain it, I need to tell you something about what is quantum mechanics. And here you might be worried because the physicists, I think, for generations managed to convince everybody that quantum mechanics is really complicated and really hard, right? That you'd have to study for many years and understand the the wave functions of the hydrogen atom and all these using very complicated integrals and differential equations, and then maybe you could understand. But if not, then just accept that particles are in many different places at the same time, and nothing is definite until you look, and everything is crazy, and there's spooky action at a distance. Okay, well, I think that it is actually, because I'm not a physicist, I can let you in on the secret, which is that quantum mechanics is actually much, much simpler once you take the physics out of it. Okay, the way that we tend to think about quantum mechanics today in quantum computing and quantum information is that it is just a certain generalization of the rules of probability themselves. Okay, so if you like, it is it's almost a level beneath physics. It is like an operating system that the known laws of physics run on as application programs. Okay, but so what is this operating system? If you asked a mathematician, who knew nothing about physics, to just invent something that was like probability, but where instead of probabilities, which are real numbers between 0 and 1, for some reason you wanted numbers that could also be negative, okay, or that even could be complex numbers, let's say, I think that they would basically be forced to reinvent quantum mechanics, right? And to me, that is really the core, right? Anything you've ever heard about the weirdness of the quantum world, either it was wrong, or if it was right, then it was just another logical implication or application of this one change to the rules of probability. Okay, so the most famous illustration of the new rules of probability, well, new since 1926, let's say, is what is called the double slit experiment. And if you won't take it on my authority, you could take it on Richard Feynman's, that he used to say that everything in quantum mechanics is contained in this one experiment. Okay, and this is the experiment where you shoot photons one at a time at a screen with two small slits in it. Again, this is not to scale. And you look at where the photon could end up on a second screen. Okay, and what you find is that it's probabilistic. Sometimes the photon lands in one place and sometimes in another, even with identical initial conditions. Okay, and this is the famous, God plays dice with the universe that Einstein could not accept, right? But I want to stress that if that was all there was to it, this would really not be very surprising or very troublesome. I mean, you could invent 20 theories before breakfast if you had to say, okay, the photon has some extra little tag inside of it that we don't see, a little RFID tag or something that determines which way it goes. And, okay, it consults its tag and it decides which way to go. Okay, the surprising part is the way that the probability works here, which actually shows that there cannot be those little tags. And in particular, what happens is that you find this interference pattern, so meaning that there were certain dark spots where the photon never appears, and in between them are light spots where the photon can appear. Okay, fine, so something strange is going on. Okay, but now the really strange part is that if you closed one of the slits, then these dark spots where the photon could not appear before, now it can appear there. Okay, so again, by decreasing the number of paths that the photon could take to reach a spot, you can increase the chance that it gets there. Okay? And even worse, if you now say this is crazy, so you set up so you watch to see which slit the photon goes through, then again, that changes things. Okay, then you can see the photon even in these dark places. Okay, you stop looking and then the interference reappears and then you don't see it, and then it never lands in those places. Okay, now, so people often discuss that by saying, the act of observation changes, the observed system. It forces it to become classical. But now I hasten to add that this effect has nothing itself to do with human consciousness, right? It's not important if a human is looking, or even a dog, or a frog, or anything like that. What matters is whether the information about which slit the photon went through has leaked out into the external world in any way, whether it's gotten recorded in any other degree of freedom. If that happens, then the state reverts to being classical. Okay, and by the way, that effect is called decoherence, and it is also the central reason why it is so hard to build quantum computers as an engineering problem. Okay, because if you like, the rest of the world, the environment, is constantly trying to measure your computer, is constantly interacting with it, and those interactions force the state to be classical again. Okay, but when you have a system that is perfectly isolated, like a photon that is not interacting with anything else, then you do see this interference pattern. And the quantum mechanical explanation for this is simply you cannot say the photon goes through one slit or the other. You have to say it goes in a superposition of the two slits, which means there is some complex number called an amplitude that is associated with each path that the photon could take. Okay, and to find the amplitude is related to the probability that you'll see something. We'll discuss that. But to find the final amplitude of some event happening, you have to add the amplitudes for all the ways that it could happen. Okay, and the result is that if a photon could reach a spot from one path with a positive amplitude, and also from a different path with a negative amplitude, then those two contributions can, as we say, interfere destructively and cancel each other out, with the result being that the photon is never observed there. Okay, if you close off one of the slits, then the amplitude is only positive or only negative, and that means that it can be observed. Okay, so that is what's going on here. So to be a little bit more precise, the central claim that quantum mechanics makes about the world is that if you have any object at all, and this could even be something like us or like a cat, but because of decoherence, we typically only notice this on the scale of atoms and molecules. Okay, but if you have any isolated object, let's say, that can be in two perfectly distinguishable states, being a computer scientist, I'll call the states 0 and 1. Okay, so this is what we call a quantum bit or a qubit. Okay, and physicists like to denote qubits with these funny angle brackets. They're called the Dirac-Ket notation. Okay, but this is really just a notation for, we think of these as two different orthogonal vectors. Okay, 0 and 1. Right, and orthogonal at right angles means perfectly distinguishable in quantum mechanics. Okay, but then quantum mechanics says that the system could then also be in any linear combination of the two states, which you could write like this: A0 plus B1, right, a weighted sum of the two states, where A and B are complex numbers called amplitudes, and they satisfy a normalization law that the absolute value of A squared plus the absolute value of B squared equals 1. Okay, so what are the possible states of one qubit? Well, if we looked at real amplitudes only, for simplicity, right, forget about the complex part, then we just have A squared plus B squared equals 1, which you may recognize as the equation of the unit circle. Okay, so these are the possible real states of one qubit, right? We have 0, we have 1, but we also have arbitrary superpositions of the two, like this state, 0 plus 1 over square root of 2, which is like an equal mixture of 0 and 1. We could also have states that were mostly 0, but only a little bit of 1, like over here or over here. Okay, now, if you were to measure this qubit and ask it whether it is 0 or 1, then you force it to make up its mind. Okay, and then the rule is that it tells you that it's 0 with this probability, like a squared, and it tells you that it's 1 with probability b squared. Okay, and furthermore, it then collapses to whichever outcome you see. So if it said that it's 1 and you ask it a second time, well, then it's sticking with its story. It just still says that it's 1. Okay, so your interaction with the qubit has forced it to decide one or the other. And at its core, quantum mechanics is a way of calculating the probabilities, that you're going to see these different outcomes as the absolute squares of the amplitudes. And I should say that you may wonder, what is this qubit? And just like in classical computer science, if you're writing a program, right, you don't have to think about the transistors, right, and that these variables that you're creating are actually voltages somewhere, inside the microchip. Okay, this qubit could be many different things. It could be an electron that could be either in its ground state or in a first excited state. It could be a particle that is either spinning clockwise or spinning counterclockwise. It could be a photon that is either horizontally or vertically polarized. Right? So, there are many, many different degrees of freedom in physics that could be used as a qubit. Okay, now what is the idea of quantum computing? Well, if you have, now we ask what happens when there are not just one qubit, but many qubits. Okay, and then, a key fact about quantum mechanics is that in general, you cannot write a state of several qubits by simply saying this qubit is in this state, that one is in that state, and so on. Okay, instead, it might be that the qubits are correlated with each other. Okay, the quantum mechanical version of correlation is called entanglement. Okay, so the simplest example of entanglement would be if I have two qubits, then maybe there is an equal amplitude for both qubits to be in the state 0, 0, or for them to be in the state 1, 1. Right? That would mean that if I measure one qubit and I see it in the state 0, then immediately I know that the other one is in the state 0, right? And likewise, if I find one of them in the state 1. Okay, this is what Einstein called the spooky action at a distance that he could not accept about quantum mechanics. But again, I hasten to add that, contrary to a very common misconception, this does not let you send a message faster than light. Okay, and the reason, that's actually a theorem in quantum mechanics, and the reason is that basically you don't get to control whether the outcome is a 0 or a 1, right? You just see that it's one or the other, but you don't get to choose. Okay, so it does let you do certain tasks that cannot be done if the qubits were only correlated in the classical way. That was a famous discovery of John Bell in the 1960s. And then the experiments were actually done starting in the 1980s, and they have proved that this, entanglement is a real phenomenon in the universe, and it is not just classical correlation, right? It is really, involves these amplitudes. Quantum computing really begins when we start asking, well, what if I have not only two qubits that could be entangled, which is strange enough by itself, but what if I had 1,000 qubits or 1,000,000 qubits, which could be entangled in some completely arbitrary way? Okay, and in that case, what the rules of quantum mechanics tell you, and they have said this since 1926. Right? And yet it is only in the last few decades that people really started to appreciate the implications of this. Okay? What they say is that to write down the state of, let's say, 1,000 entangled qubits, you need 2 to the 1,000th power complex numbers. Okay? You need one amplitude for every possible configuration of all 1,000 of these bits. So for every 1,000-bit string. Okay? That is more information than could be written down explicitly in the entire observable universe. Okay, and yet quantum mechanics is telling you that just to maintain the states of 1,000 little particles, nature somehow has to maintain these 2 to the 1,000 complex numbers, these amplitudes, on some scratch paper, that we don't see. Okay, and every time something happens to these particles, that nature has to cross off all of these numbers and replace them by new numbers. Right? That is a staggering amount of work for nature to be going to just to compute the world that we see. Okay, and the chemists and physicists have known about this for generations in some sense. They've known it mostly as a practical problem, right? That if you're trying to simulate some, molecules on your computer in order to learn about chemistry, the complexity of the simulation increases exponentially. It could double or worse with every particle that you add. Okay, this is why quantum chemistry is so hard, right? Because beyond the very smallest molecules, it just becomes infeasible to keep track of everything, even with the most powerful supercomputers that we have today. Okay, now the chemists and physicists have invented many, many approximation methods and tricks to try to get around this in practice. And the better approximation methods have even been rewarded with Nobel Prizes. Okay, but the general problem was, this exponentiality was never solved. Now, it was only in the early 1980s that a few physicists like Richard Feynman and David Deutsch had the amazing thought that, well, why not take that lemon and make lemonade from it? Okay? Why not turn this on its head? And if nature, quantum mechanics, is so hard to simulate with existing computers, then why not build computers that themselves would be made of qubits and that themselves could take advantage of this exponentiality of amplitudes and this entanglement and interference. Okay, well, of course they then face the question, supposing that you built such a computer, well, what would it be good for? And at the time, they really only had one answer to that question, which is such a computer would be good for simulating quantum mechanics itself. Now, when and if we actually get quantum computers, I still think that might be the most important real application that they would have, right? This is something with enormous applications. Anytime you want to, if you want to understand like how superconductors work, maybe build high temperature superconductors. If you wanted to design better solar cells with more efficiency, if you wanted to understand the chemical reactions like the ones that make fertilizer, right? These are all many body quantum mechanics problems, that are of enormous commercial interest, right? Many billions of dollars. And if a quantum computer could give you new insight into any of these, then that could sort of itself pay for this field. Okay, but still, the question stands. Well, can a quantum computer help you to solve any problem that is not itself about quantum mechanics? Right, and that's really what would make computer scientists more interested in this. Okay, so now the famous discovery that really, made most of the world interested in quantum computing was the result of Peter Shor from 24 years ago, which says that if you built a quantum computer, then it could factor integers efficiently. Okay, it could factor an n-digit number in actually something like n squared steps, whereas the best known classical algorithms use a number of steps that increases exponentially with n, or actually with the cube root of n. Okay. Now, why is that such an important problem? Well, for better or worse, the security of almost all of the cryptography that we currently use to secure the internet is based on the belief that factoring is a hard problem. Right, anytime you see the little padlock icon on your web browser, right, you are relying on factoring being hard, or some closely related problems being hard in order to secure your data. Okay, so Shor's discovery made many people interested in quantum computing who had not been, so the NSA and so forth. Okay, now of course people then ask, well, so where are we toward actually building a quantum computer? Well, I'm proud to say that after decades of research in this subject, I mean, quantum computers have been used to factor 21 into 3 times 7 with high statistical confidence. I think that 35 is soon on the horizon. So scaling this up, is very, very difficult, as I'm sure you've heard. The main reason being the decoherence. Okay, that somehow to build this, you need to keep your qubits incredibly well isolated from the external world so that they maintain their quantum superposition state, without it collapsing. Okay, but then also the qubits have to be very strongly interacting with each other. And not only that, but in a precisely arranged way to do your computation. Okay, so it's an enormous engineering problem. In fact, there were even, many respected physicists in the 90s who said this is impossible. You will never isolate quantum states well enough to do this. Now, what changed most people's view was another fundamental discovery from the 1990s, which was called quantum error correction and quantum fault tolerance. Okay, and with that said, it was that to build a quantum computer, you don't actually have to get your qubits perfectly isolated from the environment. You only have to get them very, very, very well isolated. Okay? And once the level of decoherence and of interaction is low enough, then you can use very, very clever quantum versions of error correcting codes to take one logical qubit and encode it across the collective state of many physical qubits in such a way that if any one or any few of the physical qubits are to leak into the environment, then the information you care about can still be recovered from the other qubits. Okay, and furthermore, you could even do computations on these encoded qubits. And if the error rate is low enough, then you'll be fixing more errors than you create eventually. Okay, so we're not yet at the crossover point where this error correction works and where it starts making things better and better rather than worse and worse. Okay, but we know what error rates would suffice. If you look at just 1 or 2 qubits in isolation, people can already achieve the needed error rates. This is new. This is as of 3 or 4 years ago. Okay, the challenge today is to maintain those low error rates even as you integrate 20 or 30 or 50 qubits in the same system. Okay, that is exactly what Google and the other companies are trying to do right now. They're trying to build a chip, well, in Google's case, that would involve 72 qubits, okay, with controllable, interactions, and that would also maintain the low error rates. Okay, if so, it might or might not be useful for anything. But I'm optimistic that if a 72 qubit chip works, at least it could do something faster than a classical computer. I don't say something useful, but maybe not. But something that would prove the point. And for me, the number one application of a quantum computer has always just been to disprove the people who say this is impossible. Okay, everything else is just icing on the cake. Okay. Okay, but now, what could a quantum computer do? There's a very, very common misconception in almost any popular article that you'll read about this subject, okay? And the misconception says, well, look, a classical computer just tries one possible answer at a time, right? Because it's made out of classical bits. But a quantum computer can go into superposition and just try every answer in parallel, and then somehow just immediately pick the best one, right? If this was true, well, that would be really amazing. That would sound just like those science fiction computers that I told you about before, right? It would also mean we wouldn't have to think so hard about, what to do with a quantum computer. You just try every answer in parallel, okay? But unfortunately, it is not so simple, okay? And let me explain why. Okay, it is true that with a quantum computer, you could easily create a superposition over all the possible answers to your computational problem, which could be, say, the traveling salesman, some problem of, optimizing a flight schedule, or solving a Sudoku puzzle, or, any problem with some immense number of possible solutions. Okay, you could create an equal superposition over every possible answer. The problem is that for the computer to be useful, at some point you need to look at it. Okay, you need to measure its state. And if you look, not having done anything else, the rules of quantum mechanics say that all you will get will be a random answer. Now, of course, if you just wanted a random answer, you could have picked one yourself with a lot less trouble. Okay, so the entire hope of getting a speed advantage from a quantum computer is to exploit the way that amplitudes work differently from classical probabilities. Okay, the idea with every quantum algorithm is to choreograph things so that for each wrong answer to your problem, some of the paths leading there have positive amplitude and others have negative amplitude. So on the whole, they cancel each other out. Whereas for the right answer, you would like all of the paths leading to that to have amplitudes of the same sign, to be pointing all in the same direction, so they add up. Okay, if you can arrange that, then when you measure, the right answer will be observed with a high probability. And if it's not, you could just repeat until it is. Okay, so that is what quantum algorithms are all about. So nature gives you a very strange hammer, and it was not until the 1990s that people really figured out what nails that hammer could hit. Okay, and and Shor figured out how to do it for the very special problem of factoring numbers, which happens to be what most modern cryptography is based on. In computer science, we can take any idea and we can associate to it an inscrutable sequence of capital letters. So my former advisor, Umesh Vazirani, and his student Ethan Bernstein did that in 1993. They defined a class called BQP, bounded error quantum polynomial time, which consists of all the problems that are efficiently solvable with a quantum computer. So Shor showed that the factoring problem is in this BQP class. It generalizes the classical P of what you could efficiently solve with a classical computer. I drew it with this wavy boundary because everything quantum is spooky and weird, right? But importantly, today we do not believe that BQP contains all the famous NP-complete problems, which are sort of the holy grail of computer science, right? And that would include, the traveling salesman and, most of what you want to do in industrial optimization. Okay, so it looks like there are also problems where even a quantum computer would need a long time in order to concentrate the amplitude on the right answer. Okay, so factoring is not thought to be one of these NP-complete problems. It has very special structure that makes it so useful for cryptography, but that Shor was also able to take advantage of to solve it with a quantum computer. And today a major research area is to invent new forms of public key encryption that would give us the same advantages, but that would be hard to break even with a quantum computer. And there are some good candidates for that. Okay, but the real, so one of the biggest questions we ask in this field is, well, how much can a quantum computer help you for solving NP-complete problems? Okay, and we know something about this. There's another famous quantum algorithm called Grover's algorithm. Okay, and what this does is that anytime you have a space of n possible solutions to a problem, and you can check each solution to tell whether it's correct, then a quantum computer can find a correct solution, if there is one, in about the square root of n steps. Whereas classically, of course, you would need about n steps if, all you can do is guess solutions randomly. Okay? So, but we also know that in this abstract setting, Grover's algorithm is the best that you can do, even with a quantum computer. Okay? So if you don't know any more about the structure of your problem, then even a quantum computer will need square root of n steps. So if n is 2 to the 1,000 power, then square root of n is 2 to the 500 power. Right? So it's better, but it's still very large. So what this means is that if there is a fast quantum algorithm for NP-complete problems, it will need to somehow exploit their structure. Okay, so this brings me to the last thing I'll talk about, which is that there is a famous proposal for a quantum algorithm that would try to exploit the structure of NP-complete problems to solve them faster. It's called the adiabatic algorithm. It's, if you've heard of simulated annealing, it's sort of like a potentially quantum-enhanced version of that. So it's not an algorithm where we know how to prove theorems, showing that it always works, but maybe it sometimes works. Okay, so some of you may have heard that there is a company called D-Wave that spent hundreds of millions of dollars and got a lot of popular press for, building special purpose quantum computers, which actually already have about 2,000 qubits to try to run this adiabatic algorithm. Okay. Unfortunately, now, experiments, D-Wave sold a few of these machines. Experiments have been done on them, and they do not seem to be giving a speed up over a classical computer. Okay, many of us predicted that from the beginning, but no one was listening to us. Okay, now there are it could be that the qubits in this machine are just not good enough. They don't maintain their quantum state for long enough. But in addition, even if you had a perfect quantum computer, we don't really know how much speed up you could get by this adiabatic algorithm. The running time depends on something called the minimum spectral gap. This thing here, this gap between these two lines. If this gap becomes exponentially small, then the algorithm needs to be run for exponential time. Now, Ed Farhi, who is the inventor of this algorithm, tells a wonderful story that he once went to an expert in condensed matter physics because they have lots of experience with these spectral gaps. And he said, based on your experience, do you think that our gap will be decreasing polynomially or exponentially with the size of the problem? And the expert thought about it. He said, I think it will decrease exponentially. That was not the answer that Farhi wanted to hear. So he said, what's the physical reason for it? And the guy thought about it more, and he said, well, it's because otherwise your algorithm would work. Okay, so it's a great story because at some point you might take the hardness of these problems as a basic principle of physics. Like the no faster than light communication or no perpetual motion machines, and you could just see what it implies for other things, right? And indeed, today we know that the spectral gap can become exponentially small. Okay, so I had some more slides, but also people think today about the potential of quantum algorithms for machine learning. There have been some recent breakthroughs on the subject, including by my student, Yiwen Tang. I can tell you about that if there's questions, some work on quantum supremacy experiments. We've been able to apply our knowledge about the limits of quantum computers even to other subjects, including understanding the black hole information problem, okay, of, Hawking's information loss problem. But let me just give you an executive summary at this point. So exponential quantum speedups, if you want them, depend a lot on finding a problem with a special structure where you can really choreograph this pattern of interference. Sometimes we can find that structure in problems that we care about. Code breaking, maybe some machine learning or optimization problems, but we're not really sure. Certainly quantum simulation. We can also find smaller Grover-like or square root speedups for a much wider range of practical problems. Optimization, planning, constraint satisfaction. For me, the single most important reason to build this is just to disprove the people who say it's impossible. But also, I hope it will give us a new tool for simulating nature and maybe some other useful things. Okay, thank you.
Dr. Scott, thank you for such an interesting talk. Todavía tenemos 5 minutos para preguntas y respuestas. ¿Alguien tiene alguna pregunta que quiera expresar?
Moshe? Yeah.
So, essentially, one way to summarize it, that this is a way we find a way to take advantage of superposition.
Yes.
What about entanglement? Is there a way to take advantage of
Well,
entanglement?
so pretty much every quantum algorithm is also taking advantage of entanglement, right? And that is part of the story of what's happening.
No, but I want
Yeah.
spooky action at a distance.
That. Okay. Well, I mean, so entanglement can be used, yes, to do certain tasks that are that you can't do classically, right? I mean, in some sense, that is exactly what Bell discovered in the 60s. For a long time, his discovery was considered completely useless, right? It is, only, it is important because it proves the reality of entanglement in our universe, right? But there's no reason why you actually need to do the measurement that, violates his inequality. 10 years ago, we learned that it actually is useful for something. For example, it is useful for generating cryptographically certified random numbers, which is something I talked about yesterday.
But Turing machines are based, the one essential idea of Turing machine is local updates.
Right.
Locality is very important Turing machines.
Yes.
Can we build Turing machines using entanglement
that
have this far away update and somehow will get speed up from that?
So the problem is that, quantum mechanics involves this entanglement, which is very non-local, but then the updates that happen only affect 1 or 2 qubits at a time. And if you're only looking at the other qubits, then you will not see the effect of those updates because of this no communication theorem, the fact that entanglement cannot be used to send messages. Okay, so you can absolutely define a quantum Turing machine. In fact, that is exactly what Bernstein and Vazirani did in their seminal paper in 1993. They defined a Turing machine with a superposition over different, sets of strings on its tape. So, the tape head was also in a superposition of locations. Entangled with the memory content and so forth. Today, we normally just dispense with that, and we just talk about a classical algorithm that outputs a description of a quantum circuit, because that is just a much simpler way to talk about it, and Yao proved a theorem that says that it is polynomially equivalent. Okay? But, yeah.
I have a simple question.
Yes.
A simple concern about everything we have learned about algorithms and data structure. We will have to throw away everything if we move quantum programming.
Mm-hmm.
How different is the area of quantum algorithms, data structure, programming, and so on?
Yeah, that's a great question. I mean, people have been thinking about this subject for more than 20 years now, right? And I would say that for a long time, a reliable strategy for generating a paper was to just take any topic in computer science whatsoever, data structures, communication complexity, Byzantine agreement, could be, authentication, could be anything at all. Just put the letter Q in front of it and then see what happens, right? And sometimes, something totally new happens, and that's interesting. Other times, it's, mostly the same as before, but then it requires a new proof. To prove that nothing goes wrong, even if your adversary can be quantum or whatever, or something like that. So it is a huge subject, but I would say you can rest easy that everything we have learned in classical computer science is extremely relevant. Okay, because often what you do is you start with a classical algorithm and then you say, how could I use quantum to speed up some part of it? Like, could I use Grover's algorithm inside of it to speed up some step in the algorithm? Or, you just say, well, let's just take the known classical protocols and we use them as our starting point. Say, are these protocols still sound in a quantum world, right? And there is a small field of quantum data structures, right? And how do you organize things in a quantum memory? There's not, and I think, for the most part, we've seen a lot of the same sort of limitations as you would have with classical data structures, right? Because with qubits, it's not like you get this magical random access that you can just access any component of your superposition, right? You can only make a measurement that gives you this probabilistic outcome by this defined rule, and your only choice is that you can choose in which basis to make the measurement. Okay, so it's a very subtle thing. You can sometimes use it to store information in better ways in special circumstances for special problems, and I'll be happy to tell you more about that on offline if you'd like. But then even to get those sorts of advantages, you would, in addition to a quantum computer, you would need a quantum memory. Right, you would need a memory that could, let's say, store enormous numbers of qubits and and give you random access to them.
What are the problems that are intractable with a quantum computer?
Okay, yeah, so excellent. So, okay, first of all, as I mentioned, like a quantum computer will certainly not solve the halting problem or make it computable because, anything that a quantum computer can do can also be done by a classical computer merely with exponentially more time. Okay, so it doesn't change computability. But more than that, it has only a limited effect on complexity theory, right? In particular, if we go back to this picture, this diagram that I had, so the NP complete problems are the big, huge example of the problems that we don't think a quantum computer gives you an exponential speed up for, right? And that includes most optimization problems that people try to solve in real life. As far as we know, we can get a quadratic speed up for these problems using Grover's algorithm. But more than that, we don't really know. Maybe the adiabatic algorithm will sometimes give you a bigger speed up, but it's not going to do it in every case, right? It's just like classical heuristics. You'll probably have to just try it out and see empirically how well it does. Okay, so we will still be up against the monster of NP completeness. Okay, but even beneath that, there are other problems that are not thought to be NP complete, like finding short vectors in lattices. Or people have thought about it for 20 years, but still nobody has found a fast quantum algorithm for that. That is why many people believe that cryptography based on lattices may be a very attractive thing for us to switch to if quantum computers ever come along and they break our existing cryptography, right? We could switch to lattice-based encryption, which at least seems secure even against quantum computers, so far. Okay. Also, graph isomorphism is another famous problem that, we now know how to solve it in quasi-polynomial time with a classical computer, but we really don't know how to do any better even with a quantum computer. And that's even though people have now thought about that for 20 years. Excuse me? Yes. Yes, so that's another very interesting region. So as far as we know, we don't know whether BQP is contained in NP. We don't know, right? If it isn't, that would mean that there are problems that a quantum computer could efficiently solve, but where a classical computer could not even efficiently check the answer, let alone finding it. The only way to check the answer would be using another quantum computer. Okay, so so actually simulating quantum mechanics itself may be a very good example of a problem with that sort of behavior, right? It's not exactly a decision problem or a language, but it's a problem with this sort of behavior. If you are willing to talk about sampling problems, which are what I discussed in my talk yesterday, then we have excellent evidence that there really are problems with this sort of behavior. Boson sampling and the problems that I discussed yesterday, they really are like this. If you could verify the answers, then the polynomial hierarchy would collapse. Okay, but as for decision problems, we don't really know if this region is populated. We can show that relative to an oracle, it is. Okay, and actually just a few months ago, there was a big breakthrough by Ron Raz and Avishai Tal, where, building on earlier work that I did, but I was not able to complete this. Okay, they showed that there is an oracle relative to which there are problems that are in BQP, so a quantum computer could efficiently solve them, but that are not even in the entire polynomial hierarchy. Okay, again, that's relative to an oracle. One can show that. If you don't know what that means, don't worry about it. But, yeah. Well, okay, well, what it means is that there is some evidence that quantum computers could still get an advantage over classical computers, even in a hypothetical world where P was equal to NP. That's a way to think about it.
Once again, Dr. Aaronson, thank you very much for being here with us.
Thank you.
Para continuar,